Welcome, everybody. This is going to be introductory machine learning, or machine learning for people in a hurry, inspired by the Neil deGrasse Tyson book. It's going to be a lightning quick introduction to machine learning. We're going to be talking about the foundations of machine learning and looking at a little bit of code, how you can get started at this event. So first and foremost, who is this random man at the front of the room talking at you about machine learning at 11:30 at night in Waterloo? I'm Michael. I'm currently completing my last year in computer science at the University of British Columbia, so way out west. Flew a red eye last night, so feeling really wide awake right now. I've worked at some places, and I thought I would highlight mostly as a software engineer. I am not a machine learning engineer. I'm not really a data science, to be honest, but I'm really passionate about it. I've learned a lot about it through coursework. I've TA'd classes on it. And about a week ago, the Hack the North organizers were so kind as to let me know that they needed an extra workshop on IntroML. And so I stepped up, and I'm really excited to be here in front of you all. So why attend this workshop? Why stick around? Why not just leave right now? Well, I'm sure you've all heard of ChatGPT. It's a very real thing. It's impacting basically all of our lives and passing MBA exams. So probably good to get a sense of what this whole AI thing is and get a sense of the fields. Beyond just generative AI, self-driving cars are a real thing. This past summer, I went to San Francisco for a weekend, and I was blown away seeing self-driving cars just blow by me on the street. They're here, and they're coming, and so it's probably good to understand the technology that makes them tick. And there are some scary, real ethical implications with AI. I'm sure a lot of you are familiar with deepfakes. How many people know what a deepfake is? Basically, everybody in the room. It's scary, it's real, so it's good to get a sense of this field. As a show of hands, how many of you guys are in computer science directly? How many are you in, I don't know, maybe machine learning, data science, something similar? Business? Something I didn't name, shout it out. High school? Hell yeah, hell yeah. That's good. How many of you are in high school? Okay, awesome. Oh, a ton of you guys. This is awesome. I'm so happy you're all here. So it's great you're getting started early. So I assume you've all stayed in the room, so you're as excited about machine learning as I am. So first, I want to lay out some goals for today. Firstly, let's get a sense of what machine learning is and how it can be applied in the real world. Also, some machine learning fundamentals. In this workshop, I am not just going to run some code to build a neural net. I know that would be cool, and then I could just send you on your merry ways. You get 99 accuracy, and you'd win Hack the North, and you get all cool prizes. But there are some key fundamentals that we need to understand before we can just start throwing data at models and making crazy predictions. And then beyond that, let's see and interpret some real code. I'm not just going to show you slides, even though I'm mostly going to show you slides. I don't want to, but I kind of have to. But we're going to see and interpret code for how machine learning models work. And so that way you guys have a little bit of a starting point as you go into the weekend. So our agenda for today, it looks long, but it's going to go by really fast. That introduction is done. And then we're going to get into hands-on machine learning. I'm going to walk through what the machine learning problem is, introduce how to read in data, wrangle data, I'll explain what that means, build a model, tune a model, evaluate a model, and then deploy it in practice. And then finally, I'll leave some time for a wrap-up and Q&A. Also, there is a code repository that's linked to this worksheet. And so at the end, I'll save some time to go through some setup stuff and help debug. And of course, I'm around for the whole weekend. So if you are working on running some machine learning stuff, you want to run the notebook that I linked in the hack pack, then you can just message me on Slack. You know my name. I'm here the whole weekend, and we can work on that together. All right. So firstly, let's frame what machine learning is and why you would use it. So the goal of machine learning, kind of redundantly, is to let machines learn. So in the world, we have a ton of data. That's what's made machine learning possible. We have, I don't even know how many Google searches go on every year, and we have a really good sense of what people are interested in. We have banking data. We have just data points all over the place. It's been a huge explosion, right? Big data is here, and we can't, as humans anymore, walk through all of that data. So we introduced machines. And thankfully, to couple this explosion of data, there's also been a huge explosion in compute. So it's kind of an unfair question to the high school students, but if you know, that's awesome. How many of you have heard of Moore's Law? Yeah, awesome. Okay, lots of hands. So basically, compute is scaling somewhat linearly. It's kind of hitting a plateau now, but that's fine. That's for Intel engineers to worry about. For you guys in machine learning, you can just run stuff like crazy with CUDA on GPUs and make these crazy big trillion parameter models like ChatGPT and do really cool things. And so we have tons of data. We can take advantage of it with a lot of compute. And so using statistics, we can let machines detect patterns automatically in data. That's the goal of machine learning. So the machine learning problem is to create a function. So with a function, create a new function that takes some sort of observation. So this could be like an image on the internet, prompt with ChatGPT, or a row in a table, which we'll see in this example, and then generate insights from it. So make some sort of prediction about the data. So kind of meta, but we're working with functions to create a function. Again, fundamentally, all the machine learning models are just taking a bunch of data, analyzing it in some way, and then producing a new function. In this set of slides / in the Jupyter notebook that I've linked on GitHub, we'll try to create a model to predict the output of a tic-tac-toe game. So kind of a simple, fun example. Honestly, a little bit trivial because there aren't that many tic-tac-toe games. With the memory we have available today, you could just memorize all of the games. It'd be totally right. So I'll get that out of the way initially. But it's a fun toy data set to work with, and will give us a real-world case to frame the rest of the workshop in. So there are two main sort of streams of learning that we can have machines do. The first is supervised learning. So in this picture, ignoring a lot of the labeled terms, the big thing I want you to take away is that with this initial data set we have here on the left, we have labels. So all of these emojis have either a dog or cat label. We're going to feed them into our machine learning function. That's going to give us another function. That's our learn function F. And then based on unseen new data, so some brand new emojis we have here on the right-hand side, we're going to make some sort of prediction. But the key here with supervised learning is that initially we told it what the right answer was, right? We knew that, okay, this top emoji in the first row in the training data is a cat. So when you look at a new example, you kind of have a rough sense of what a cat is. Okay, so that's one sort of big stream of machine learning. The second that comes with that is unsupervised learning, where we give it sort of a scramble of data with no labels, right? We just have this single here column X, and it's just a jumble of emojis. And we're going to feed it to a different sort of class of algorithms. This, in this example, is a clustering algorithm. It doesn't have to be. We'll get a new function, again, like a function that creates a function, and it will group everything together. Now, I don't really like that this picture has labels on it with dogs and cats. That's where we as humans have to decide, based on those groupings, what we think they are. So in the real world, this looks like taking a bunch of customers, trying to group them together in maybe some clusters, and then saying, okay, based on this cluster, what do I think this person is like? Is this like the elderly lady that comes really early to the grocery store and shops? Or is it, a mom who's like buying lots of stuff for her whole family? And like, how do I take advantage of these clusters in pricing items, placing things in a grocery store, et cetera? So this is unsupervised learning where we have no labels on the data. So this is the overall picture of machine learning engineering. It's super overwhelming. But what I want to highlight is, for a lot of folks in the room, you probably have some vague interest in becoming a machine learning engineer. How many of you want to eventually maybe work in machine learning? You're here because you're interested in a career in that path. So a lot of folks, and me included, get into this thinking, okay, like I want to do some fancy neural net stuff. I'm going to build some crazy models. I'm going to do some really crazy math, and that's going to be my life. But this entire top part that's sort of highlighted in yellow all has to do with data. So it's data exploration, validating the data, wrangling, which we'll talk about later, like cleaning the data, and then monitoring and improving the data over time. All that isn't really stats heavy. This has to do with like data engineering at your company, tapping into new APIs or new data sets that are available, new columns, asking your product team, hey, can we start collecting birthdays? Can we start collecting gender? Can we start collecting other things? And that will probably improve your model a lot more. All this really cool stuff at the bottom that we'll talk about, like model engineering, model evaluation, releasing the model, that's all fun. That's where the really cool stuff is. That's where the latest research is. But again, what I want you to take away from this workshop is that you are limited by the data. So if you walk out of here and you go, okay, I want to build something really cool for Hack the North, I want to build a model to predict something awesome, you need to find a great data set. And the more data you can find, the better that data is, the better your model will be. So if you take away anything from this entire talk, it's that this yellow data pipeline stuff up top is the hard work. The red stuff is the fun, the stuff we like to talk about with our friends, the accuracy, like 99% that we like to report, but it really starts with the data. It's all about the data. I did some word art. There you go. Okay, so this is the data set we're going to be working with today, or is in the notebook that you have available that you can work with after. So initially, it comes in with all of the different board positions. The X's are, of course, an X in a tic-tac-toe board. The O's are an O. And there's also blanks. Those are B's. You can see some examples here on the right-hand side. And then the final column on the far right is the class. That is the outcome of the game, so the final result. So positive means that X won. In this case, we're just assuming always that X moved first. And so yeah, you can see some rows from the top half of the data. From the bottom half, I call tail there. This is the initial data we're working with. Again, our goal is to take from these first 9 columns, learn about how tic-tac-toe works, learn maybe an effective strategy. That's not explicit. We can't really look at it exactly. And then predict the outcome of the game. And again, with the caveat, you could just memorize it in real life, which is important to know when machine learning should be applied. But again, this is just a toy data set. So with that, let's talk about how on earth did I read that in? How could we even get started? So again, remember, it's all about the data. Please think hard about your data sources and try to access lots of them. Common examples you'll find in the wild are CSV files. This is comma-separated values, basically just a spreadsheet. Sometimes you'll work with Excel files directly, and there are packages for you to do that. You can even work with databases. So for a lot of folks, SQL is probably new, but you can sometimes pull data directly from a database, which is especially useful when you have huge amounts of data, like petabytes of data. Excel files very quickly break down. And new is web scraping. So, ChatGPT is basically trained on the entire internet. And that was done a lot in part due to web scraping. A lot of you might have seen Reddit's API changes. Do you guys see that? Show of hands. So Reddit decided to make their API a lot more expensive, and the community decided to black out. And a lot of that came from OpenAI very smartly realizing that Reddit's real world conversations were some of the best training data ever. And so OpenAI rubbed their hands together, scraped it all for basically free. I don't know what it cost. And then now they're very, very rich. They're worth, I don't even know how much now. And Reddit didn't really benefit from that. So web scraping can also be a very powerful tool. If there's no API, no data set available to you, you're not out of luck. Down here, I link a few examples of places to find data. UCI is the University of California, Irvine. You can Google UCI datasets, and they have a website with a whole lot of datasets that can serve as initial inspiration. Kaggle, how many of you heard of Kaggle before? Awesome. So you're way ahead of this workshop. That's a website. It's kind of like a competition platform, also a way to see different common data sets and what people have done with them. Great resource. I highly recommend if you're interested in machine learning, make an account, get on there. And then also GitHub. GitHub has all these really cool repos that are awesome lists. And there's one I found for awesome public data sets. Again, just another resource. And then finally, I should have put it on here, but you're at a hackathon. This is a really cool opportunity to get novel data sets. Companies often, for sponsor prizes, will release a data set and say, hey, please make a cool model with our data, and we'll give you some money, a prize if you do so. So I recommend after this workshop, go to the sponsor booth, be like, hey, RBC, you have any data? Do you mind? And who knows, maybe you build something really cool based off of that. So again, data sources are abundant. The first library you'll work with when you start to read in data is called Pandas. How many of you worked with Pandas before? Awesome, good amount of hands, half the room. This is Python's ubiquitous library. It's used everywhere for reading and manipulating data. It's honestly super straightforward. At this point, you could just, hey, ChatGPT, how do I read in this data frame? Or how do I read in data and get a data frame? And it will just spit out code for you. So I wouldn't worry too much about the nitty gritty. The one term that I want to introduce that you'll see a lot if you're new to Pandas is a data frame. This is just Pandas' data structure for data, tabular data. So often you'll see this pattern in code where it's some table name, like mine in the data set is tic-tac-toe, and then _df. That's a good convention just to let people know, hey, this variable is a data frame, and it's going to be storing some data. So again, your model is going to be a panda chewing up a lot of that data. I want to walk through, again, I've talked a lot about tabular data. What does that look like in practice? So we have this first set of columns, and these are going to be your features. So age, job, city, rating. These are different features available to you. The final column, what we're trying to predict, is often called the target. So in our case, that's the outcome of the game. And then each row we typically refer to as an example, an observation, a whatever. Tabular data is really effective for this kind of thing. You can see why spreadsheets and CSV files are a very natural fit for machine learning. Models really like them. They work well with them. And so often we're going to try to get our data into this tabular format. So you can see in our example, just kind of one more example to really drill in the terminology. In the red box there, we have, anybody know what those are called? All the columns, but not the last one. Those are exactly. The blue is the target. I think I'm aiming that, right? The target. And then in green, we have an example or an observation. Exactly. So it's good to have that terminology down because you'll see that used throughout the field. A brief but important note that I'm really going to gloss over, but could be an entire talk on its own, is EDA. This is short for exploratory data analysis. It's the process of looking at data and basically getting a feel for it, like vibe checking your data. This is really important. If you just blindly, again, go in, take your data, throw it at a model, you might get good accuracy, but you also might make your model a lot worse for no reason. The reason we want to do EDA is to see existing patterns in our data as a human. So I could like correlate two variables. I could look at maybe imbalance. So do I have a lot of times X winning in my data set and not a lot of times O winning, or like a tie for the tic-tac-toe example? And it's really important to understand these things, as I'll touch on more later. But yeah, and data visualization is really key. If you want to work as a machine learning engineer, you're going to have a boss. He's going to be like, hey, we have all this customer data. Can you at least give me like an initial feel for it? And being effective at creating good visualizations is a key skill. Now, one hack I'll give you is that you don't actually have to do a lot of work for EDA these days. There are a lot of libraries that allow you to just do automatic EDA, which is pretty nuts. So you should like learn how to interpret the plots, and you should learn EDA stuff. But again, you can take that in university. You can take that. You can watch YouTube videos. It doesn't really matter. But if you want to quickly get started to hack the north, don't make like a million plots. Just use a package like YData profiling. This used to be called Pandas profiling. And you can like run this on the data frame, and it will automatically create all kinds of cool plots. It will show you relationships between variables. And then you'll see, oh, actually, I think the like top right square in the tic-tac-toe board is really useless. Like if I play there or I haven't played there, it's not going to inform my model. So maybe I'll drop it. Or maybe I notice that two features are highly correlated, so I don't really need them. They're kind of redundant, and I'm going to be feeding my model the same information twice. These sorts of things, as a human, you can do to really level up your models before even getting started. And again, to reemphasize, data is everything. The more data sources, the better you clean the data, the better you pre-process it, the better you understand it from EDA, the better your model is going to be. All right, so that's all data reading. Any questions at this point? We're making good time, which is good. We are, again, skimming like that entire workflow, like that really crazy slide I showed with the yellow at the top and the red at the bottom. We're walking through that very fast, which I apologize for. But I want to give you a total sense of like what the machine learning workflow is. So over the next 36 hours, you can sort of like execute on that. No questions so far? Good. Keep plowing along. So the next section, wrangling. I like this term. I'm from Alberta, so just wrangling makes me think like cowboy. It's just making your data tidy. So first, before I want to talk about tidying your data, I want to talk about a really key concept. So in all this, we need to like assess our model. I'm sure you guys have seen like a machine learning model gets 90% of like cancer diagnoses accurate. And you're like, wow, 90%, that's so cool. How did they get that really cool number? We need to be able to like assess these things to report to other people, hey, I made this model and I think it's actually really useful. You should use it in your hospital, in your lab, in your et cetera. But like, how do we do that? We have all this data and we're training our model and all the data. Like, what do we test it on? We could just hope. We could just pray. I'm going to train it on all of my data and see how it goes. And for some things, we are kind of doing that. Like ChatGPT, we're just sort of like training it on all the text in the world and then just seeing how it does. And I mean, it's obviously doing really good. But for some things like cancer diagnoses, we really do need a number. We need to know how effective is this model. So thankfully, there's a better way. And that better way is data splitting. So what we're going to do is, and you saw this earlier in the slides, but I kind of ignored it, is we're going to create test data. So we're going to take some fixed proportion of our initial data set, and we're going to hold it and put it away forever. All right. This data cannot be used at all to influence model training. And I'll say this one more time. At UBC, in our like machine learning courses, they often call this the golden rule of machine learning, which is sort of silly because no one calls it that in the real world. But I think it's good to think of it as a golden rule that you like never break. Your test data cannot ever influence your training process. So for example, if you like visualize all of your initial data and then you learn something about your data from that, well, and then you split it after, your test data influence that initial visualization stage. That's bad. That's one easy example. There's some more subtle ones that you can see. And this leads to like bad academic papers that get peer reviewed and slashed, and it's really bad. And I don't want that to be you. So please, I just really want to drive this point home. Your test data must be held separate. Then we're going to take our training data, build the model, go through this entire workflow, and then finally produce a score with the fittingly named .score function in scikit-learn, and in most libraries it's similar. And then we're going to report that statistic. This is what people are talking about when they say my model was 90% accurate. is reporting that final score on the testing set. All right, so once you get data, I want to talk about tidy data, what that means. Like, how do you assess if a data set is good? Do I have to do any work to like clean it up at all? There's this definition that I'm pulling actually from Data Science 100 at UBC, and it's the following. You don't have to read all this text, but the source is there, which is good. It's that each row is a single observation, each column is a single variable, and that each value is a single cell. So there are lots of like subtle examples of how this is broken, but what I want to drive home is that it's what you classically think of as good data, that each single cell in your spreadsheet, in your table, in your whatever, is just one singular piece of data. So you have some like super long date where it's like 2001, October 10, blah, blah, some day. That's bad. There's like lots of things going on there. It's probably better to break that down. Or you could represent it as a timestamp or something else. Or if you have like a ratio in a cell, some really complex string that has like a bunch of data encoded in it, all bad, not tidy. You have to do a lot of work as the engineer to break that down to make it useful for your model. So tidy data, each row is a single observation, each column is a single variable, and each value is a single cell. Make sure to set up your data for success. Sometimes we also have to transform data to make it useful for our models. These models, I keep throwing this word, it's just math. Like under the hood, they're just doing a lot of math, scary math like linear algebra and statistics and stuff that gives me PTSD for my classes. And so we have to do some transformations to it to make it accessible to these models. So sometimes, for example, the models will rely on distances. So you can imagine we have a model of, say, like points in space. We have like, 1, 0 and 0, 1 and so on in a Cartesian plane. And we want to build a model based on how far these points are away from each other. If we have units in different scale ranges, that's going to be a problem. So you can imagine trying to correlate someone's like height and weight. Height is obviously the range of like, say, like hundreds of centimeters, and weight could be much different. If it's like in kilograms, it could be a little bit smaller, or if I scale it up, I could really impact my model. So scaling numeric features is a simple example of how wrangling is often important. Another one is instead of having numeric features, sometimes we have categories. So for example, in our tic-tac-toe game, each of the cells has one of the categories assigned to it of 0 or O being an O being played, X for an X being played, or B for it being totally blank. Our models don't know what to do with strings. They get really confused, they get stressed. So we have to do some sort of re-encoding to make, again, those string values, those categories, into numbers. And what we'll do is called a one-hot encoding, or an encoding, to change each of those categories to a binary column. So just to give you an example of what this looks like, this, again, is our original data that I showed a lot earlier in the slides. And what we do when we encode it is we take each column and then each category in that column, and it becomes 3 unique columns, each with a binary value. So initially, we started with top left square, and it had x0 and xo and b. And then now we get 3 new columns, top left square underscore b, top left square underscore o, and top left square underscore x. And now they're all binary. So it's true if in the original column it was true. So you can see in these first 5 rows, we had no b's. These are all zeros. We had an O and O in the first and fourth rows. So here's a 1 and 1. And likewise for x. That makes sense? That's like one example of an encoding. And there's lots of these, and they're kind of nuanced. And I have to go pretty quickly. But hopefully that gives you a rough sense of how you can re-encode data and make it accessible to your models if it's a category. Any questions? Cool. I think it's a fun one. Scikit-learn, I highly recommend you use scikit-learn for your projects if you're just getting started with machine learning. There is lots of fancy stuff out there. There's PyTorch, there's JAX, there's all this stuff. You won't need it for this weekend if you're just getting started. Scikit-learn has all the models you'll need and all the pre-processing steps you like. And they have a really, really nice interface for wrangling data. The first is a pipeline for combining all of these like initial transformation steps with your final model into one like end-to-end pipeline. So first, maybe you scale some features, then you encode some features, then I finally fit my model, which we'll talk about shortly, and then I score it. Pipeline will kind of smush these all together into one nice function call. And then a column transformer is another tool that scikit-learn gives for doing different transformations by column. So here you can see an example of a data frame. We have city, which is an array, titles, which are text. We have expert ratings, which are numbers, user ratings, which are numbers. These all need to be transformed in crazy ways. And in scikit-learn, we have this really nice column transformer thing, which allows us to define, OK, for my categories, I want you to do a one-hot encode. And for the title column, I want you to do count vectorizer, whatever that is, right? You can Google all these things later. And for the remainder, I want you to drop those columns. And then I want you to fit and transform all of that data. So if we want to go column by column and do different things, we have some numeric features, we have some categorical features, we can do that. There's much more to say on this topic. Like all these things, I'm very much so skimming them. Other ideas you can think about and might be relevant to the data sets you work with this weekend are missing data. So what happens when we have a row and a couple of the cells are missing? What happens if an entire cell is blank? What happens if a row is blank, a column is blank? What do I do? Feature selection and feature engineering. So I'll just say a sentence on each of these. They're really important. Feature selection is what I sort of hinted at earlier in the EDA portion. It has to do with choosing which features out of my data set I'd like to use the most, which I think will be the most relevant to my model. And then feature engineering is the broad process of combining features, transforming features in unique ways to, again, make them more effective to my model. So sometimes this is like taking two columns and like dividing them by each other. So for example, if we had like housing prices and square feet, maybe they're both interesting on their own. Perhaps our models learn better from them if we do like price per square foot. It's like one sort of easy example. Again, each of these deserve a lecture on their own, and they'll make you much stronger machine learning engineers. Frankly, today, a lot of the big money is in feature engineering. So it's an interesting topic, but again, sort of limited today. And to drive home, your model is only as good as your data. So do not skip this stuff. Do not go straight into your model at Hack the North. Do spend some time transforming it. All right, now we're at the juicy stuff, actually making a model and talking about some sort of like real world machine learning models that you could apply. First, I want to talk about a baseline. So if you knew nothing about machine learning, I just gave you honestly no information about a new observation. I told you for any tic-tac-toe game that's played in the entire world, what should you predict as the outcome? How do we know that? So for a tic-tac-toe data set, we actually have 65% of the examples of X, the first player in the game, winning. So if I didn't tell you anything about the tic-tac-toe game whatsoever, and I force you to make some sort of prediction, who should you predict winning? X, obviously, right? So this is sort of our baseline. We should definitely do no worse than 65%, right? We obviously would guess that our model should at least get 65%. If we're doing worse than 65%, we're doing less than a very like rudimentary case. 50% would be no worse than guessing, right? So it's good to have these baseline numbers in mind because, and I'll talk about this more in a bit, but if we had a model that was highly imbalanced, so say X won like 90% of the games, and then I made a machine learning model and it predicted the correct winner 87% of the time, if I tell it to you without any context, no baseline, you're like, 87%, that's pretty good, that's an A. But if you put it in the context of some sort of baseline, you're like, that is trash, right? I can't even do as good as just the most obvious strategy to begin with. So keep that in mind. Do that first. Before we had machine learning, I mean, there's lots of ways you could start, but one easy example is something called expert systems. So people would sit down with like doctors, say, and interview them for hours and hours and hours and learn about, based on this symptom, you should make this diagnosis, and based on these combination of symptoms, you make this one, on and on and on. And they would code this into these horrible nested if-else crazy statements that were super hard to maintain, super hard to work with, but actually did perform pretty well. So they would interview an expert, save all that information, put it into code. We actually have machine learning models that work quite similarly today, and that's the first model we're going to start with. So before I get into this, how many of you guys recognize this? Quite a few. Okay, so I want you to try it. I want you to find somebody beside you, hopefully somebody you haven't met, but if you met them, that's cool. I want you to go to this URL, akinator.com. I want you to think of a real or fictional character and have it try to guess who you are. We'll do this for like 5 minutes, but I just want you to get a sense of like what this thing is because it'll help set up the next section. Yeah, which is nice. All right. If you can hear me clap once. If you can hear me clap twice. Okay, so how many people, Akinator, guessed what you were thinking? Yeah, it's pretty good. So Akinator, it just asks you lots of questions, right? It gets like, it drills down more and more and more and more and more. So you can see how it sort of parallels those expert systems that I mentioned on the last slide. And we actually in scikit-learn have a classifier that works super similarly. So instead of, again, to set up, go all the way back to the beginning of the presentation, we have way too much data. We can't interview our data, our like petabytes of Google search history. It's just impossible. So instead, we need a model to learn rules automatically rather than interview experts. So here's an example where I try, again, just some ish scikit-learn code to fit a decision tree classifier to our data, like build a model, basically. Now, here I do it on the untransformed data with like strings in it, as I mentioned before. And you can see it freaks out. So I've caught this exception. If you've never seen Python before, it should be mostly self-explanatory. I'm trying to run this, and then I'm doing something bad, and it says, OK, you could not convert string to float. So I'll help you scikit-learn. I'll make them floats. I make a pipeline. This is what I mentioned earlier. I can sort of combine all of my nice column transformations, do my encoding, and then put my classifier in the end. I fit it to my data. I can see some example predictions here. They look pretty good. And then I score it, and I got 100%. So I guess I'm done. I can go work in NVIDIA or OpenAI, wrap it up, right? I mean, I got 100% on my data, so I think that's pretty good. This is the tree that we made. So I don't know if you guys can read that. I can't. There's a lot of layers, obviously, right? This is for, I think it was like 600 examples. This hugely massive tree that's really, really complicated solves tic-tac-toe. Awesome, right? Like I don't know. It gets 100%, so what else would I need to do? Does anybody think there are problems with this?
Okay, so this tree automatically generated, or is it like generated manually?
Generated automatically. So it's going to, based on, there's different ways you can do it, but it uses information theory, which anybody know about information theory, like entropy and stuff? I'll say fun tidbit I'll just mention here. There's a really cool video from 3Blue1Brown, which I bet a lot of you know. 3Blue1Brown, yeah. Where he talks about the optimal Wordle guess using information theory. And that same math is how this happens. But so yeah, it's automatic. Yep. Is this bad? Do you think it's bad? You think it's bad. Why do you think it's bad? So that's also bad. I mean, you can score on your training data. The training score is a real thing. You're right that it's not super helpful. Like I couldn't go into the real world and be like, hey, I solved this problem. Especially not for like serious things, right? Like cancer predictions. I just am testing on examples. I showed my model. In the most trivial case, you're right, it could just memorize them. But also here, like, does anybody else feel that tic-tac-toe is really this complex? Like, should it be this hard, right? Maybe not. So what I want to, and this is how it starts. So we can learn a little bit from the tree. This is, I just kind of zoomed into the very top. Interestingly, the middle square is the most important move in tic-tac-toe. A lot of you hopefully already know that. When you start, you should always play in the middle square. This model proves it. But again, the complexity is just not awesome. The goal of machine learning is to generalize to new data. So you're totally on the money. Like our training score isn't really that important. I shouldn't be bragging that much about 100%. And like your gut should tell you a model this complex just won't generalize well. There's like better ways we can talk about this, but like just as an instinct, how is that going to generalize well? The term we use in machine learning lots is overfitting. So that's building a model that is too specific to the training data. It's learning way too many of the idiosyncrasies, way too many of like the fine details of our training data. And so it's just not going to perform well in real life. To give you guys a better example, a lot of you guys are mixed high school university students. When you study for exams, how many of you use practice exams? All of you, hopefully. If you don't, that's bad. You should start doing that. Your teachers suck. If you have used a practice exam before, you could imagine just like taking it and memorizing all the answers. Like question 1A, you don't even read the question. Just 1A, 2B, 3, 1.49. And then you show up on test day, you get 100% on the training data, right? You memorize all the exam questions and their answers. And then you show up on the exam and you fill in 1 as A, 2 as C, 3, 1.49. And then you get like 0, or you maybe get 1 out of like just luck. That would be bad. You overfit to your practice exams, right? You memorize the exact answers, and that's not what you wanted. You wanted to learn the concepts, the general things, the not too specific things, so that way you would generalize well to the test day. Does that make sense what overfitting is? This is a key concept of machine learning, so any questions, now's a good time. Seems like we're good. So let's contrast that really complex model with a decision stump. So let's limit our depth of the tree to just be 1. We learn a very similar start to the tree. We also get the middle square. And this model, I tested it on the test data, gets 70%, which is already 5% better than we had on the initial baseline, which is pretty sweet. And it's, again, a lot less complex. I could take this to my company and say, hey, boss, this is the model I built. It's not that good, but it tells us a lot about the problem, right? So if you want to play tic-tac-toe, you should move in the middle first, and then you'll win, maybe more often. So this is how we merge those two things together. We have this super complex tree that does really, really well, but doesn't generalize. And we have this super short tree that's kind of dumb. And that builds us to this graph, the most important graph in all of machine learning. So here on the bottom, we have the decision tree depth. So this is our stump, what we just looked at. And this was our super crazy complex tree that you could barely see on the slide over here. And what we see as a general pattern for all models ever, basically, is that we have some sweet spot where a model gets somewhat more complex. We minimize our training error. So it does matter to look. We do want to see our training error not be totally crap. And then we get good test error as well, which is good. Now, the problem, I want this sort of bottom here, where I have low test error, and I don't start to have this really bad case where I have my super overly complex model that's overfit. But how on earth could I figure out what the best test data is? This is all 100%. This whole region, I'm going to see this same training score. So how do I know when to stop? How complex is complex enough? We need some way to be able to sort of proxy the test error without actually using the test set. Like I mentioned, we can only use the test set once. That's a really important rule. You cannot be okay, I'll just pretend that I'm starting again and use my test set on a new max decision tree depth. And then, okay, I'm just going to delete that workbook because it didn't do very well and make a new workbook and pretend it's a new test set, but you're really just running the test set over and over and over again. It really is important that you just use the test set once. So what do we do? Anybody have any ideas initially? Anybody have any, what could I do to proxy the test set? Tough question. Yep. Yes, very good. What was your name? Michael. So that is awesome. That's called cross-validation, and that's what we do, exactly on the money. So we're still going to save the test set initially. Say 10%, I like that number. We'll save that data, only use it once at the very end. But then what we do while we're choosing our, say, maximum depth, that's called a hyperparameter. While we're choosing some value to tune our model, we're going to save a portion of our training data again. That's called our validation data. So we're going to take a subset of the training data and use that as a pretend test set over and over and over again. Does that make sense? Yeah. So again, on each depth, we'll train on a subset of the training data again, and then use the rest as mock test data. And this should, if you study some statistics and you learn about random sampling and so on, it should reasonably approximate the test error. That's the goal. So just a bit of terminology I want to introduce now because it's relevant. Parameters. This is you guys have probably done some sort of computer science stuff before. You've probably seen function with its parameters or arguments. In machine learning, that's what the model learns. So we never write parameters. The decision tree splits, those are going to be our parameters. Those are automatically learned. That's the whole point of machine learning. Hyperparameters are the controls we get to make. So we still do inevitably set some what we want to call parameters, but now they're hyperparameters because we're making a function that makes a function, right? There's a sort of meta thing going on. And so our hyperparameters are going to be things we can control about our model to, say, limit complexity, other things like this. So far, we've just seen decision trees. So it'll be the depth of our decision tree. All right, now moving forward from that, again, very brief introduction to cross-validation, but you have to do it. Now we want to evaluate our model and see, is it any good? We've talked about this a bit, but again, what I want to talk about is accuracy. So accuracy isn't everything. Accuracy is the number we've been talking about the whole time. It's what percentage of the predictions were correct in the end. So remember that baselines thing I talked about, 65% of tic-tac-toe games are won by X. They can be quite high in practice. Your data can often be unbalanced, imbalanced. So an easy example is disease. If you're studying some disease, most of the folks in the world probably don't have the disease and you want to study lots of data. unless it's COVID, which at this point, I don't know who hasn't had COVID. So the imbalance in your data is going to be quite high in practice often. And there are lots of techniques for this. And one of them is changing what our metric is. So for initially we had accuracy. We were just saying how many did we get correct. But we can actually do a lot of really fancy stuff. And I'm not going to dwell on this because it could be like, again, a whole course. But there's a lot of other things we could look at. That's the whole point of this slide. There are two that are common. One is called precision and one is called recall. And they each emphasize different parts of what you would care about the most. So with disease, maybe it matters a lot that we don't want to make false negatives. So we don't want to say somebody doesn't have the disease when they do, right? It would be really bad if somebody came to the hospital and we were like, we ran our machine learning model. We said, you're healthy. Great. You can go home. And they were sick. So if we use, in this case, I'm pretty sure it's recall, then we can more carefully train our model to handle that case. We can say, our model, we really don't want to get people, send people home when they are sick. So we're going to choose this other metric instead. Precision's a bit different. Now, again, I can't dwell on this slide, but I'm leaving it here in the deck for you to Google and explore. And if you have imbalance, this is where to start. There are other things, and you'll learn about like upsampling if you do some Googling and other things. Those are like kind of bad. You're like just manipulating your data in like fake ways. This is a good place to start. So if you have imbalance at Hack the North, that's where to get started. Bonus, I just want to talk about regression. Has any of you heard the term regression before? Quite a bit of hands. Okay, awesome. So instead of predicting a class like we've been doing in this entire deck, here you just be predicting a number instead. So you're predicting like housing prices, or you're predicting any sort of numerical value. The metrics and the model will change, but the fundamental concepts do not. So that's the emphasis of this intro machine learning workshop, is to get a really good foundation. So you know what overfitting is, you know about this like trade-off between complexity and how well your model will generalize. But the metrics and models are all that change. So instead of studying accuracy, because you can't, you'll study things like RMSE and all these things, and you'll Google them and you'll figure them out. And scikit-learn will honestly take care of the hard work. These fundamentals will still apply. So if you do regression instead at Hack the North, no big deal. You're already machine learning pros. All right, and then last but not least is just a note on deploying. So one big problem you'll have is you'll sit down at Hack the North and you'll be like, Kate, I went to this really cool ML workshop. I'm going to be the ML guy this weekend. You guys do the front end and the back end. I don't care. That web dev stuff, that's below me now. I know machine learning. But you have to make your model useful, right? If I build a really cool model and my friends can't use it, then we're kind of hooped. And we're going to try to demo. And then the machine learning model doesn't talk to the back end, doesn't talk to the front end. And then Hack the North is over. So instead, I just want to talk really briefly about how we can make our model useful. One common option is to deploy it via an API. There's actually a sponsor this weekend that I didn't know was a sponsor until the opening ceremonies called Bento ML, and they do a lot of this like for you. So if you're curious, go to Bento ML's booth. Maybe you can get a job. Maybe you can learn about more about how their tech works. But yeah, how many people are familiar with an API? Awesome. This group, you all are experts. Y'all are experts. So you can use an API to deploy your model. If you're not familiar, it more or less means taking your model, deploying it to a web server, and then having a URL let you like access the model. So you can, via going to a URL, just like you go to a normal web page, instead you'll send data about like a new observation, and what you'll get back is a prediction. So you can do that for your model, and then your teammates can call your API, and you'll all be groovy. No one's panicking. Your demo goes awesome. So this is, I asked ChatGPT because I was curious. This is what that code can look like. This is an example like Flask route, if you've seen an HTTP framework before for like a server-side language. And a lot of the code is the same. Like what I really wanted to highlight was this middle section. We're doing the same thing we're doing in the notebook. We're calling like model.predict, but all this fluff around it is like web dev stuff. So if your web dev friends can get rid of all the fluff for you, then you can just worry about reading in your model and making a prediction on new data, which you get from them. So that's you can deploy your models, basically. In the notebook at the tail end, I've mentioned a library. It's called JobLib that can help you export your model to a file and read it in, which also can be helpful for versioning and deploying on, like, say, a separate code base. Okay, I also want to make one note. This, again, should be a whole separate lecture, but it's to remember your impact. So models have impact in the real world. You should really think about the ethical impacts of your machine learning models. For example, you've all heard of ChatGPT. That company is called OpenAI. They're not very open anymore. And they deployed that really fast, right? And really quickly, and just kind of dropped it on everyone and scaled it up. And I think there are pros and cons to that. I think it's a very nuanced thing. But I encourage you all, as young engineers who will go change the world, to really think about what you're building, what factors it uses. There are like real world consequences. I'll just paint one quick picture. You can imagine an ML system you build for whether or not you want to give somebody a loan, right? Whether or not you want to let them take a mortgage on their house for a certain amount. And if you build in certain features like race or gender, you could reflect systemic injustices that exist in our world today, right? If you use data from the current world and you believe that the current world reflects certain like systemic inequalities, which it does, and you expose those to your model, it will learn them and reflect the same injustices that exist, right? So you want to be very careful about what data you give your model. Again, this harkens back to feature selection, feature engineering. Really think about like what you're telling your model to learn, because it will learn it. Like these are it's just math. It's not a human. It's not making good decisions. So do be conscientious of that. All right. I think with that, I want to give you some directions to point in for like more exciting stuff. Because I know a lot of you probably came, you're like, I'm going to learn deep learning. I'm going to be able to build ChatGPT at the end of this workshop. Unfortunately, that wasn't the case. Nobody can. Well, but maybe you could after Hack the North. But I do want to talk about some trends just so you know where to go from here. I want to do cool stuff. So 2 things. One is that deep learning is in. So deep learning is a complex technique that involves using lots of like hidden layers of neural networks and really scaling up our models hugely. And this is the dominant framework. Now, decision trees, which we talked about, are obviously not like cutting edge, but there is a related technique called random forests, which it sounds similar, right? Trees, forests. They actually just use a ton of decision trees and use like randomly sampled features from your data. And they're like really effective. Like companies like Uber have used these for years. Like lots of companies. Anybody that's doing machine learning, random forests are definitely in their stack today. So the decision tree stuff, even though it's simple, is actually really close to like state of the art. But like deep learning is like really, really what's in right now. So I encourage you, Google deep learning, learn some stuff. There's some more math there, but honestly, y'all are bright. You're at Hack the North. You can definitely pick it up, and that will bring you like to the cutting edge. I also like GPT, NLP. This is pretty cool. What I think is interesting about them is I talked about overfitting today, and these models use like billions to trillions of parameters as context. And you might be like, oh my God, like, isn't that overfitting? We're just fitting on everything. And it kind of seems like it is, like it defies some of the theory, but it's working, which is cool. I also encourage you to look up this transformer thing. Again, the math is hard, but it was written by U of T grad along with Jeffrey Hinton, who, if you're not familiar, is like the Google guy when it comes to AI for like a while. He's gone now because he doesn't really believe in all the generative AI stuff. It's complicated. But I encourage you to look up transformers. I think the paper is called Attention is All You Need. That's what caused all this ChatGPT stuff to like blow up. And I encourage you, give it a read. Reading papers is hard, but it's cool. And maybe research is for you. You don't have to be a software engineer. There's more to see in the world. Okay, those are 2 trends I wanted to highlight. That's basically it. Questions, comments, concerns, queries. Now is the time. Yep. Yeah, good question. I'll just repeat it for everybody in the room. If you want to get better at machine learning, what should I do? Should I make stuff? Should I read stuff? So again, I'll first say my background as a software engineer. I really want to say build stuff. That's always what I tell younger students. If you want a cooler job or you want to like learn a new framework, just get in the arena and build the damn thing. Build a new project using that technology. With machine learning, I think it is a little bit different. Like I think some hands-on experience is good, especially initially. It's more fun that way. Go build stuff, build cool models, and deploy them. And always deploy your work, like always make it visible on the internet. That's like the best thing ever. But then, yeah, you should take some classes, go on Coursera, go on YouTube. MIT has OpenCourseWare. Go take a class at a university if you're in school, because there's a lot of math, there's a lot of stats, and without a really solid foundation, it's hard to get into this stuff. So you should learn like how a neural network works eventually. You can't just like blindly throw it at stuff. So yeah, machine learning requires a bit of a mixed bag. If you're into the math stat stuff, I think this is a lot more fun. Other questions? Yep. That's actually a good question. The data set is super old. It's from like the 90s. The question was like, how did the target class get made? Like, didn't humans say, you know, who was winning, who was losing? And I think, yeah, they just basically like played out the games, and there was like a certain optimal strategy, so they like knew if a position was won or lost. There also is like it's negative if it's a tie or it's unclear, but like a winning position is only positive. Yeah, I hope the way the model was built, or the data set was built, I mean, is that X was only positive when it was like absolutely winning. Like, you know, some chess positions are like one, like engines can be certain, like it is. And I hope it was in that vein. I'm not absolutely sure, but I'm pretty sure. And it's a toy example, really. So, yeah.
So something is called a table. So do you believe that the AI could one day like create like table base, and then use this table base and then build upon it, so the AI would one day solve chess?
Table base I'm not super familiar with. I do think AI is crazy though, and it's coming for everything, so you should be ready for that. That's what I have to say. Yeah.
Like table base is a specialized database. That is does not involve machine learning.
Okay.
So one thing like a machine learning software is if the machine actually reaches like a position can be used using the table base, the machine will just use table base.
We should chat about that after. I'm down. I'm down to learn more about it, but I'm honestly not super sure. Any other questions, folks? Yes?
I just want to be clear.
Yeah.
So overfitting.
Yep.
Does that come about as a result of using the same exact data, or using quote unquote too much data?
Too much data is never a bad thing. So that's a good point. You won't overfit from too much data. You'll just get better models. You always want more data, more columns. All that stuff is good. Obviously, like sometimes columns can be redundant, so that's why we do like feature selection, feature engineering. But yeah, to your point, more data is better. Where overfitting happens is learning too much about the idiosyncrasies of the data. So imagine you have some outlier and you memorize that. That's going to cause problems. And a lot of this has to do with what hyperparameters we pick. So we control the complexity of the models, right? With the one example we saw, decision trees, you have the depth. Every model that you'll access in scikit-learn, or really ever, you have access to controlling how complex it's allowed to be. With a neural network, the number of hidden layers, you can control if it's really, really deep or really shallow. And that will influence how training goes and if you overfit. So it really comes down to complexity. That's kind of the key. Yeah. Yep. It's $1 million question. Yeah, I mean, there are some red flags that people use. The kinds of error we looked about before are the key. So I want to pull up that graph again. So when you start to have this huge gap, that's when you know you've overfit, right? That's what this red line is sort of indicating. But it's hard to know sometimes. Like there are going to be some cases where you're not really sure if you're here and there just is a gap, or you're here and the gap is bigger than it should be. That's why we do cross-validation. Cross-validation, you can have quite a bit of confidence. So it's really important to cross-validate so that you're picking hyperparameters that are actually good. Other questions? A couple more minutes. Yep.
Is there like a soft spot for a certain number of layers using one, for example, like we were doing this example,
Yeah.
which kind of parameters are necessary to keep?
Yeah, I mean, there is no silver bullet. Like, there's no typical value to use. It just totally depends on how much data you have available, class imbalance, what features are available. If the data is tidy, like all these things sort of influence how complex you should make your model, that sort of thing. All right, I think folks are ready to go. It's 12:30. Thank you all. You've been wonderful. If you have questions, feel free to come up. But yeah, see you at Hack the North. Thank you.